So what actually is differential testing? I'm just chatting here. So like the formal definition of it is like saying like it's a software technique that compares outputs of different implementations. You have like, for example, one functionality or one kind of specification that you want to achieve, and you have different implementations of that specification, and you compare those different implementations. And you know, like this is actually where it comes from the name. You try to figure out what's the difference going on. Like if these implementations are correct, they're supposed to be no difference. They're supposed to be exactly the same. So basically that's differential testing, which can also, I think, called comparative testing. I don't know. I think so as well. But anyway, like in Foundry or in Solidity, we call it in that sense a differential testing. So let me share with you my screen. Okay. So you can see my terminal, I guess, right?
Yes.
Okay, that's great. Just want to make sure. Uh, okay, so let's get started. Oops. Oh, I'm already here. Okay, sorry. Okay, so in order to actually explain differential testing, just need like those 10 minutes to walk you through something here, which is called FFI, which actually stands for Foreign Function Interface. Have you come through this before in Foundry, the FFI option? Somebody has seen it before?
Yes, I think so. I've seen it.
Yeah. It's really something cool in Foundry while you're doing the force testing. It's it basically stands for Foreign Function Interface, which the idea of it is to make you interact with the outside world. Like you're not just testing your Solidity contract, you can be actually doing something else from outside. And in order to show that, I will just show just simple examples from the tools we know from Linux, like the commands we know from Linux, like echo or cat or whatever. So I think everybody knows what echo is. Echo is just like printing out something in the screen in Linux. So what I have here is I will just, this test here, test FFI for echo. So what I'm doing is writing a command, an echo command, echo something. So I'm creating an array of strings in Solidity, and I'm putting the first element of that array to be the command itself, the Linux command, which is echo. And the second element is the thing that I want to print on my terminal. That's whatever it can be. And then the interesting part comes here. If you see my pointer, I hope you can see my screen here. This result here. So what does it say here? The vm.ffi, which is this thing we're working for, it will run that command to your onto your terminal, and it will return to you something that you can decode as a result. So now this result should be the output of the terminal. Like whatever the terminal spits on the screen, you should be taking in this result. And naturally it is bytes. So like any question till this part? I think it's simple. Okay, so FFI basically enables you to run a command and get the return value that actually comes out of the screen of the terminal. So it comes by default as bytes, and you need to decode it. So for example, I can be decoding it as a uint, or I can decode it to anything. I will show you actually, it assumes, Solidity assumes that whatever output from the screen should be a 32 bytes. So that's why while I'm decoding it specifically to UN256, which is a 32-byte integer, and then I can whatever do like here, just print the decoded value or whatever it is. So let me just run it for you here. So forge test. Uh, so, okay, that file name is okay. Sorry. Oh, I have many examples, so that's why I like got confused with the name. So this way I should be running the test, but as you all know, this test requires calling something from the outside world, which is FFI, which is the foreign function interface. In that sense, I have to write this option, FFI. So if you forget that, the Forge, the founder is gonna scream at you like, hey, there's something here missing, because it will figure out that you actually required to do something like foreign function interface and you didn't specify that option from the beginning. So I have to do it. So now I run it. Yeah, just ignore that one. I'm just checking the echo for now. So you already just, this is the command I run, echo, and that number. And then this is the raw result that comes out at bytes. And then I decode it to integer. And of course, you all know this is written as a hexadecimal, and it converts to an integer to become 16, right? So is there any question for this part? So you will all know how to use FFI. Yeah, that's good. Everybody thumbs up. Okay, cool. Okay, so I can just show that quickly. Another example, which is a cat. We all know cat, like it just presents like to you a file that you have. In that case, I'm having a file called address.txt in my test folder, and it just contains, it can contain a list of addresses, but I'm just writing one address in it. And I'm doing the same thing, just cat, that file, and then I take the result. And this can be useful because you can be having a file and you need to somehow like read that file into your tests to use the entries in it. So you just take the result and decode it into an address, and here you go. But there's something interesting here I want to show you while you're doing this, as this test runs here. So when I run that that cat command on the address, I actually wrote the address in the file as a 32 byte, because this is something that can get you to be like confused a little bit, because if you write it like in this way, it can actually get confused. So I actually wrote it and I paired zeros in it to make it 32 bytes, and then the Forge will figure out while you're decoding it. So let you figure out, yeah, like, hey, this is an address because I decoded it as an address, and address is a 20 byte is a 20 byte variable. So I'm just converting that 32 byte to a 20 byte variable in a sense. So that's basically the first part. This is just how to use FFI, because right now can do something more interesting. I will just move to just close this. Oops. Okay. So how do we actually use that thing here? If you are having like a function that is written by a different programming language, you can be having different implementation of the same thing that you're doing in Solidity in your smart contract. For instance, I can think about if somebody is building a token with certain, complex tokenomics, and he made that model using a language like Python because it's good with mathematics, and then he decided to move that to his smart contract, and he wants to compare that implementation in the smart contract to the model that he already built in Python. So this can be something like that. So you basically need to compare the two implementations, and in this sense, you are comparing two functions from different languages, from different programming languages. So this example is just a simple way to explain that. I will be just comparing the add in Python to the add in Solidity. So I have that function here in Solidity, which just adds two unsigned integers. And I have that function in, and I have that test that basically compares the output that comes from Python with the add function that is here in Solidity. And let's take a look. Oops, what's going on? And let's take a look on how Python is implemented here. Yeah. Okay, you can see what Python here is doing is just taking two inputs from the command line, the X and Y, and it adds it together, and it encodes it so that the Solidity can read it. Like this is something you can find easily, like in the ETH ABI library of Python, because as I told you, from the Solidity perspective, from the smart contract perspective, you're gonna be running some command through the vm.ffi, and then you're expecting an output. But you should be expecting that output in a certain format. And I showed you, like, for example, it should be like 32 byte in the first case. And also here, like, you're gonna be doing some decoding basically. So I just converted to a hexadecimal and I encoded as a UN 256 and all that kind of stuff. This is important to do. Like you have to consider that, like even if you have a function to that you're comparing with, you have to wrap it in something like that. So in the end, you print that result to the terminal, because that what you print is just it's not that you are printing it for yourself, but you're actually printing it for the FFI to read for the Solidity smart for the Solidity test, because this is the output that result is gonna pick up. So let's take a look. So basically this is how it goes here. As I told you, in order to write the commands, you're just typing the command in an array, in a string array. You first put the, like these commands are separated by spaces. So I put here like first command is Python, because you run a Python, a Python runtime, like a Python program, basically. And that program is called add.py. And these are the arguments of the program. So these are just the two numbers that I'm adding up. Okay. So these numbers, where do they come from? A and B, they come from here. They come from the input to the test function. So what values it's gonna have, you expect? Like, can you answer that?
It's
Can
like
somebody answer?
it's like a fuzz testing, right?
Yes, exactly. That's right. That's why it's actually built on fuzz testing. This is absolutely true. So basically, this is like it's gonna depend on the runs that you have on your Foundry. Oh my God, why does it do it all the time? So you have here. So I'm actually using a fuzz configuration here, because yeah, it's a differential testing, but actually relies on some fuzzing that you do. Because if you are testing two different implementations, you want to test those implementations on different values. If you are doing unit testing, you will be just testing that on one value that you are enforcing, which is meaningless. You want to test as much values as possible. So yeah, so A and B is going to be random variables coming from here, but they are going to be constrained by being 32 bits, and we're going to see why lately. And then I run that through the FFI interface here, FFI command, sorry, from the VM, and I take the result, and then I decode it. This is the result from the Python program. Then here I make a solidity add, like this is the output of the add function in solidity, and I want them both to be equal. That's how I'm comparing both programs in both implementations in solidity. So let's run, I guess. I'm gonna make that match test. What's its name? Test contract versus Python. Okay. So I'm just testing a contract implementation versus Python implementation. Okay. So there is no problem. It made supposed to make 16 runs and nothing is no issues here. You can notice I enforce it to be 16 runs, and I think most of you know why. All of you actually know why. Because like here you are actually you are executing a command outside through the terminal in your Solidity test, and this actually consumes time. So despite this is 16 runs that should be done instantaneously, it took like 3.5 seconds here, 3.4 seconds, sorry. And so like if you're doing like the fast testing that we usually do, we should actually be doing bigger number, and we consider that. So this is just for demonstration purposes. But if you are doing that, you can need 1,000 run, for example, and you just leave your PC doing it, and you come back to see the result. So that is just because you have to know that it takes time to actually execute something like that. Okay. I'm expecting this workshop will not take much time, so don't worry, because I write all these examples already. Don't want to do like the last workshop. You have another example here. I'm comparing with TypeScript. This is the same thing here. Like I'm having another implementation for the addition in TypeScript, and I'm putting all the commands in a string array, and then I'm doing the same thing in Python, and I'm comparing the results. I did even forget something here. Like I run here like this is the TS inputs. I copy the same thing. It should be around pi inputs, but because it's basically like seriously like this is the same procedures that you're doing most of the time, even with different programming languages. So let's see actually how the TS, the TypeScript program is working. So add the TS. Oh, sorry. Add the TS. Okay. So you have here like the TypeScript program is taking two arguments, which is A and B. That is in the command line itself, and it adds it together, and then it decodes it. Like you don't forget that step. You just I'm importing ethers. I think we all know ethers JS. I'm importing it. It has a default ABI coder, and it encodes the result from the TypeScript to become UN 256, and it spits it out in the screen because this is what the FFI is taking in the test. This is like just a way of communicating with my test. Like it's not meant for myself, as I told you in the Python example. And in the end, you have your test. There's something here I need to, yeah. Yes. That's really a good idea. Chris here is having something I didn't even think about it, but this is just really a neat way to integrate Foundry with hard hat. Like you can imagine here, like instead of these commands, I didn't try it, but I think we can do it. I think we can do it. You can run a hard hat command here instead of that TS node or whatever it is, and you take the results from hard hat or you need to console log or whatever. You know, you can figure it out. Like you can just take what is printed down the screen, you parse it, and you do that kind of test. So like if something you don't have, like for example, there are things in hard hat that is possible and right now might not be possible in Foundry. I remember something like, for example, when you have a stack too deep problem, you can actually do something in hard hat that bypass it, but in Foundry you can't. So you can run that test, for example, in hard hat, and you integrate that test into your Foundry. So yeah, that's a really good idea. So I want just to make you notice something here. It was not noticed in the Python example, but it can be noticed here clearly. You have the way the command is passed, like npx ts node, and you have the add file of the TypeScript implementation, and then you pass the arguments, the numbers. These numbers you can see here are the index is 3 and 4. If you go to the TypeScript, you can see it's 2 and 3. And so somebody can figure out why it is happening, because you know, like you're supposed to write something like this, npx ts node. This is the command you write in the terminal, literally. So one here is like is like the third number if you start from 0, and 2 is like the fourth, but I'm writing it as 2 and 3, not as a 3 and 4. So why this happens? Somebody can figure it out. Yeah. Okay. I will have to say that because these are the kind of errors that can actually make you annoyed a little bit, because it might be not clear to figure out. But we know, like npx, what it's doing, actually it is just kind of syntactic sugars in a command line to make you call the commands that are inside the node modules. So what it's actually doing here, it just gets removed to call like node modules and whatever, and then it gets ts node. So this can be really annoying if you don't know it. So in the end, npx ts node are actually one thing together. So it runs like, this is the zeroth element, this is the first, and this is the second, the number is the second, and this is the third. So you know, like you need to know this, because it happens, like under the scene, behind the scenes, and you might not have any idea about it, and you're stuck for 30 minutes, and in the end, it's actually something very trivial. Anyway, yeah, that's the suffering. Okay. So any questions so far? That's cool. So right now, what we've just done is called an external differential testing, which is trying to compare an implementation that is written in Solidity. In that case, it's a very simple implementation for an addition, and some implementation in another programming language that you need an FFI interface to call it. Something before I go, I just forgot. It's good that I didn't forget. You see here, you notice here, I restricted the inputs to be in 32 bits. I can restrict it actually to be more than that as well, but I will make it 256. And what do you expect will happen here? Somebody can answer this, please? So right now I can have like a very, very big numbers, A and B. And then I run Python addition on it, and then I run Solidity addition, and then I need to assert that they are equal. So what do you expect will happen?
Can overflow in the Python program.
Yes, right. Like, well, TypeScript, JavaScript, Python do not expect like 32 bytes number usually. Yeah, you can do that. You can implement that in a certain way in Python, but I think in this construct, it should complain. So yeah, that's very obvious. So like you can see here, like it took some addition, like yeah, cannot be, no, I don't know, like no, this is not the error I mean, but anyway, you can see here the counter example that throws this error. You can see the number is very big. This is a number that Python cannot handle. And you can see like in the call data itself, this is supposed to be the function, and then you have ff, like this is crazy, like Python will just complain. So if you want to do it, you can, I think you can make some Python implementation that handles big numbers like that. Or if you don't have that implementation already, so you need actually to constrain that in your Solidity already. You can do bound, you can do, you can constrain it like in the type of the data itself, but you have to put that in consideration. Okay. Oops. Um, so we did external testing. Now I will demonstrate something in internal differential testing. I think I have it here. Demonstration. Yeah. Oh yeah. Okay. That is actually an example that I added lately to this workshop. I actually prepared this workshop last month, and this example I added lately because I saw that example in one of the audits, and I think it's really cool to see something that we deal with every day. So I just picked up some functions the client did, and I made some changes. It's not the same actually. But we need to focus here. Okay, I want to delete this. Don't want to confuse you. Okay, so this is basically the implementation here. We are concerned about a variable, a storage variable called global time threshold. And client have a function that basically updates that global time threshold. But he updates it in a very quirky way. He says like, well, if your timestamp right now is bigger than global time threshold, sorry here, so you need to update that global time threshold in a loop by adding a certain value, a kind of, it's a cooldown window, until you reach your block timestamp. So you just add up, add up, add up. You can do that like 10 times until the global time threshold is basically reaches the block to timestamp. Cooldown window can be anything, can be like 1 day, can be 1 hour, can be whatever. So you just go through a loop here, and I think someone can tell me like, of course this is a problem, right?
Yep, gets excessive.
Yeah. Yes. Please.
Yep, it is gets excessive.
Yes, excessive. Yeah. Yeah. You're actually writing into storage. You can see here. You can write into storage each time, and it can be many times. I don't know if the compiler, if you run it in an optimized way, it can actually figure out to write in memory and then write in storage in the end. I didn't check that out. But what I'm sure about is that the optimization will not figure out that this loop can be just replaced by a mathematical formula. So of course you need to request that change, and he did another implementation here, which should have been done in the beginning. So it's basically just you have a difference between block.timestamp and global time threshold. So in a sense, you can figure out how many cooldown windows you can add. So in that difference divided by the cooldown window, you can know how many periods passed, and then you add that, and then in the end, you make that multiplication, and you have the new global time threshold. So in that situation here, we have two different implementations in the same programming language in Solidity in the smart contract, and I need to compare them to make sure that they are the same. I did some change, by the way. So anyway, I'm expecting some results here. So how do I do that? You basically declare the first contract, so it's the version 1 of the protocol, and the second contract, and you in the setup you create these contracts. This 100 refers to the cooldown window. It's like 100 seconds, and then you do the test here. Okay, so let's take a look at the test. So in the test, I need to focus here on the action. You know, when we are doing tests in fuzzing or whatever, we have like a precondition, an action, and the postcondition. So the action is where the change is happening, is where actually the things that you're trying to test is going on. So I want to test the update global time threshold in protocol v1, and I get here the state itself. Okay, arrange action. Okay, whatever. so what my target here is, like, let's go back to the contracts here. So what my target here is, I want to run that function, that update global time threshold, and effectively the global time threshold here should be equal to the global time threshold here if you run the same function at a given time stamp. Or let's say in the same state of the blockchain, you run that function here and you run that function here, whatever timestamp or whatever, in the same state of the blockchain, you need the effect to be the same. And the effect in that case is the global time threshold, because this is what changes here. So this is what I will be doing here. I will be running the action, the update global time threshold, and I will take the effect from that in protocol, the version 1 of the protocol, and I run that in the version 2 of the protocol as well, and I take the effect, and I need these two effects to be the same. I need the new global time threshold to be the same. Okay. But now I go to that line. I want the block to timestamp to be the same in both cases, right? But this is not only the case. Like, I can be having a whole state of the blockchain. I want it to be the same. For example, this function is very simple, but it can be something that queries something from Uniswap, from Aave, whatever, from an outside protocol. And I need basically the whole blockchain to be the same at the moment when I call the V1, the version 1 of the protocol, and the version 2 of the protocol. So in order to do that, I'm using Snapshot from Foundry. Like, these cheat codes are really cool. You need to go through all of them. So I will be using the snapshot here. So I'm taking a snapshot of the whole, like, EVM, which is local in my machine, of course, before I call that function, and then I revert to that snapshot again before I call the version 2 of the protocol. So basically, so that it doesn't make a difference, for example, if you call the V2 first and then the V1 later. It's basically the same thing. You are calling that function in the same state. Yeah, you kind of roll back to that snapshot. Okay. And you have here, like, because I'm fuzzing, yes, I'm warping to a certain timestamp that is given by a fuzzing input, and then I compare. So, any question in this part before I run it? Okay, that's cool. That's great, really. So, what test was this? Test compare, okay. In that case, of course, you see, I don't need FFI because this is actually internal differential testing. I'm testing both our solidity implementations. And the cool thing is they are basically, this situation is just a situation of fixes. Client fixed something and you needed to do the same thing. The point is the first implementation was just not optimized. It was just not good anyway. So I'll be running that and I'm expecting, well, there is something here and we need to debug this, okay? So it tells you here's the assertion failed, and this is the left-hand side, which is actually refers to the version 1 of the protocol, and this is the right-hand side. And you can see here the difference is something like really, really minor difference here. Like it's just 100 seconds, which is actually refers to the cooldown window. So you can figure out that it just added an extra 100 in the version 2 or something. So you know where the problem is here. It's basically an edge case. So how to fix that? I'm just actually something I changed, but in order to do that, I just changed this. So I just removed that equal sign because if I put that equal sign right now, it will go an extra. Sorry, it will. It will go that extra step. And here you can test again. And it's supposed to be the same. Yeah. So what I wanted to show you here is that, and this is, by the way, like, because this is internal testing, I didn't run against another implementation. So I can run like 10,000 runs. Here is 2,000. So there's no like time penalty to do that. So the point here is I just wanted to show you like it can spot some differences for sure to you. I'll turn it back. Okay. So any questions so far? Like regarding the test itself or these contracts? Okay, so everybody understand the snapshot. It's not so difficult, but okay, that's cool. We are kind of done, but there is some kind of a bonus example I want to show you. It's much more complex, and it's a way to use the foreign function interface. The foreign function interface will come in handy if you are doing tests that require something that you do off-chain. For example, you're testing something that includes a bridge, and when you're implementing a bridge or something, like you have some element that you need to do off-chain. So if you can do that through test, you can actually do it through foreign function interface. In my example, I'm having something to do off-chain, but it's not a bridge. I'll just show you. It's even cooler, I guess. Let me check that. Yeah, that example is a ZK. Okay, let me first explain the idea of that contract, of that example. We have a user here interacting with a smart contract, okay? And there is a problem here. The user needs to give a password. He knows some password, and he wants to call a function in the smart contract with that password. And then in the implementation of the smart contract, it's gonna be checking something like, hey, the hash of that password is equal to some hash that I have saved in my storage. And if that password is correct, then I verify that I can mint him a new token or whatever, like if he knows the right password. So what kind of problem do we have here if I'm having such an implementation in the smart contract? Somebody can tell me?
Because the blockchain is transparent. That won't be like very secure.
Yes, it's not risky. It's just like there is no risk. It just will happen. Like everybody will know the password. It's, yeah, exactly. Everybody will know the password. Like there is no risk in it. Like it's you know, risk implies that there is a possibility something bad happen, or possibility nothing will happen. But there is no possibility here. It will certainly happen. Anyway, so if you call that function with the password of the user, you know, everybody will see it in the blockchain. So what we are doing here, there is some extra step. Okay, I'll delete that. So the sorry, there is some extra step that I will do here. The user will do specifically to generate something called a proof. So what's going on here? The user in his web page or in his local machine or even from outside or whatever, he knows his password, and he will generate some kind of a proof, we call ZK proof, that says, you know what, I know the password. It's like, hey guys, I swear I know the password, and but I cannot disclose it to you. So that proof, it says that, like it says, like, you know what, I know the password, but I give you no information about it. You know, like if you have that proof, it just doesn't give you any information about the password. So basically, the user needs to generate something like that in his machine, in his local machine. So this is something that is done off chain. You can't do this on chain, because if you do it on chain, basically you also disclose your password. So you generate that proof off chain. And then in the end, you will be passing that function, but this time you will be generating a proof and something else. I don't want to call it right now to confuse you, but okay, it's called nullifier anyway. It's also like proof, but it has some other purpose. So you generate those two variables here off chain. These actually like kind of represent the password, and you need to run that function inside the smart contract. And even if everybody in the world will see this proof and nullifier, they cannot figure the password. They cannot figure out the password. So let's see how this is working. Oops. This is a kind of a big project because it includes many things. So this is the contracts part. I need the test. Okay, yeah. Okay. Ignore that first one. I'll explain it later, but need to focus on that one, on the second test. Okay, so basically what I want to say in that example is you have something off chain that you want to generate for the smart contract, but you need to include that in your test somehow. This can happen in bridges. By the way, there are bridges that use this concept also of ZK, so you can be generating proofs for bridges. You can be doing you generate that proof and nullifier, and then you run the function of the smart contract that you want to test. This is supposed to be, for example, the action here. But the thing is, the action that you are running requires something to generate off chain. Okay, so in that case, what I'm doing here is I'm passing. I'm passing. This is a password. This is supposed to be the password. Turns out it doesn't worth all this fuss. It's 1234, and this is supposed to be an address of the user. And this app is the app. This is the off-chain app that generates the proof. And this is Node apparently because this app is written in JavaScript and you need to run it through in a Node environment. I hope this is obvious, like this part. Yeah. Yeah, this is just a zero knowledge app. I know it's something complex. I'm not here trying to explain zero knowledge, but what I want to try to explain is just that if you want something to run off chain, and you don't even need to understand what zero knowledge is, you know that in the end it's something, some black box written in JavaScript or whatever that it can be written in C++ as well. That circuit compiles to a C++. That generates to you some kind of artifacts, proof and nullifier, and you need to use these artifacts in order to run your smart contract functions. Yeah, if I run that, it requires some other stuff. Yeah. So that's basically it. This is just an example that shows you how a proof looks like, because it's really a complex thing. This is an array of unsigned integers, of 8 unsigned integers, and they are big numbers, because like in cryptography, these numbers are in finite field and they are very big, so that they cannot be broken. And this is the other artifact, which is a nullifier. By the way, the point of nullifier basically is so that you don't reuse the proof. It's basically that's it. So in the end, you run that function and you're good to go. So okay, this is just a part. Like I can conclude here. Really, thank you for listening, and please tell me your questions. Yes.
Thank you so much for that workshop. That was very interesting. I'd add one thing though. I'd be very careful when a client code base requires the use of FFI, as it's effectively arbitrary code execution on your machine. So I'd encourage everybody to take the time to inspect the code and determine why FFI is used before running it. Just because I've seen cases where security firms have been popped because malicious actors are posing as legitimate clients. Yeah.
Yes. Yeah. You mean like what kind of risk? Like the risk in the test itself? How can it be?
Like a hidden backdoor, he means like a hidden backdoor.
Yeah, like hidden backdoors and stuff. Yeah.
Yeah, but it shouldn't be affecting the deployment, or
No, but like you said with the echo command just before, that's basically command line running on your machine.
oh yeah,
Yeah.
yes. You mean like if the client himself, but we can use it. That's what I mean, like as an auditor, right?
Sorry, what do you mean?
Yeah, I mean there is no. I mean the risk is if the client is using it to inject something or have a backdoor. But I mean like if we are auditing their code, like there's no risk from our side. I mean.
Yeah.
Yeah.
It's just like a warning kind of thing, because like I said, I've seen
Yeah.
cases where security firms have been popped, and also Code Arena has received code with hidden backdoors as well.
Oh, yeah, that's really important to know. Thank you. Okay, so yeah, if you have any more questions, if you don't, I think we can conclude that. We can call it a day.
Yeah, thank you very much for the workshop. It was very good.
Thank you, Jose.